We have a special talk today by Victoria Bollo, who is here at ESO, and we'll be talking about problems of AGN jets detected at millimeter frequencies with ALMA.
Thank you. Well, hi everyone, I'm Victoria. So I'm a PhD student at ESO, and I will present some AGNs just in this ALMA Cal survey. So let me start showing this plot that I'm sure many of you are already familiar with. So we know that AGN can inject energy within the galaxy and also around the host galaxy. So this could be roughly interpreted into modes. So this radiation could be inefficient, for example. These AGNs are usually low luminosity AGNs, and they're actually caused by X-ray heating. On the other way, we have also the radiatively efficient AGNs, which are usually brighter, and they can be caused by several injection of energy, for example, X-ray heating, photoionization of the gas, or radiation pressure on dusty gas. There is a way also to classify AGNs as radio-identified AGNs. So, for example, if we take here in the x-axis the radioluminosity over the optical luminosity, we can see that some objects have a radio excess. So basically, this right side of this panel shows the radio loud AGNs. And also, if we look at the AGN radioluminosity compared with the radioluminosity produced by star formation, you can also identify if this AGN this source is AGN dominated or star formation dominated. Particularly for this talk, I will focus on radio loud AGNs. I would like to also introduce briefly these classifications. So this is the Fanarov-Riley classification, also known as FR, FR1 or FR2. FR1 jets are usually low power Earth darkened radio sources. So here you have an example. So we have a bright center, and then when the emission fades away towards farther away from the center, basically. These FR jets, FR1 jets are usually low luminosity, and compared to FR2 jets, these are usually brighter. They are also asymmetric, they have high power, and they have like this edge brightened radio source. Like it seems to be like this part of the AGN is brighter than the center itself. So just keep in mind these two classifications because I will mention it at the end. Now I would like to introduce ALMA Cal. So ALMA Cal is a survey that is compiling all the calibrator data. Basically, every ALMA science project spends a few minutes observing a calibrator. These calibrators usually are bright quasars, and most of them has been classified as blazars. So we have compiled all the calibrator data from cycle 1 up to cycle 10, and we have compiled more than 30 terabytes of data and over 1,000 calibrators. So here you can see that we have different ALMA bands, and if you're not very familiar with ALMA bands, you can see here the frequency range and the wavelength range covered by each ALMA band. So the idea of the ALMA Cal project is to use these calibrator data with and study different scientific cases. For example, in a project that we performed, we looked for untargeted CO emission line search. So in this figure, you can see an example of a calibrator data. This is ALMA band 3, and we always have the calibrator, which is a quasar, right at the center of the field. But for this project in particular, we were not interested in the quasar. So we would just mask out the quasar and look around for serendipitous detections. So here particularly, you can see that at the edge of the field, we found a bright CO emission line that is zoomed in here. By doing this iteratively over all the calibrator data, most of the calibrator data we have so far, we were able to constrain the cosmic molecular gas mass density at different rates. So here in the y-axis, we have the molecular gas density, and we have it from different redshifts, and you can see the evolution of the general trend of the cosmic molecular gas. If you have questions about this work, you can ask me later, because I will not focus in these CO lines. So in this figure, you can see the spatial distribution of all the calibrator sources in the sky. You can see that there is no preferred direction. So basically, we are mapping all the southern hemisphere, just because ALMA is in the southern hemisphere, roughly homogeneously. And then when looking at different calibrators, we found some examples of jets, of extended jets. For example, here is the same calibrator observed in different ALMA bands. So here you can see in ALMA band 3 with two bright hotspots that it seems to be two side lobes. Then if we look at ALMA band 4, then the continuum of the lower part seems to fade away. And then this is the ALMA band 6 image of the same calibrator. So this is basically a very powerful sample that could help us to understand or to study different jets in different ALMA bands. So far we have found 13 jets, which are labeled here in the x-axis. So we have 13 ALMA calibrators with these extended jets. And in the y-axis, I plot here the integration time, the accumulated integration time in each ALMA band. So here you can see color-coded the different ALMA bands. So in bluish, we can see the ALMA band 3, which is one of the most observed. Then with band 6, which is this greenish, dark green. And some of them have observations also in ALMA band 9, but it's not very typical. So you can see that out of these 13 sources, this one, J1229 in ALMA Cal, is one of the most observed, the most popular calibrator that has these extended jets. Actually, this source is very popular. Maybe some of you have read about it, but it's usually called as 3C273. I don't think it sounds familiar for some of you. Okay, cool. So this source has a lot of information also in different ALMA bands. It's one of the sources that has data in all the ALMA bands. Well, now when compiling the calibrator data, we have data that has different configurations, because all the configurations for each observation have to meet the PI's request. So here I'm showing the mean resolution of all this data. So you can see that overall we reach a very detailed resolution in most of the quasars, even though in ALMA you can pick some ways in which you can combine data with different resolutions and make them consistent. So you can see that in some cases we reach a spatial resolution below 0.5, and in other cases is above 1 arcsecond, but it's still pretty good. This is the redshift distribution of all these calibrators in which we found extended jets. So you can see that most of them are below 0.5 redshift, but also we have a few that are above 0.5. There are some radio counterparts for these sources. So these sources have also been observed in radio surveys. So we were able to constrain them to 1.4 gigahertz size. I think this was using BLA observations. And you can see that most of our sample surpasses 100 kiloparsecs of size. So this would indicate that these sources have very extended emission. Radio. Now in this plot, I'm showing something very similar. So here in the y-axis, we have the 1.5 gigahertz luminosity, and x-axis is the redshift. So you can see that our sample follows a trend very similar to what has been found in other surveys. Also, this was a figure that we put together with some collaborators for a proposal. So basically, this is our sample. And we have the classification also of some of these jets as FR1 or FR2. So most of our samples seems to be FR2, but we also have a few that are FR1 and also a few of them that are irregular, so they couldn't be classified as any of these within any of these two categories. And again, this is color coded by the 1.4 gigahertz size that I already showed you. Well, in general, I just would like to highlight here that all these ALMA jets were identified in millimeter wavelengths. So that means that these jets are potentially young. This is the map. So here we have the continuum map, the continuum moment map for a source that has these extended jets. And here overlaid is the radio emission. You can also see here the 1.4 gigahertz size for this source. This is the redshift. And we also constrained some radio SEDs. And you can see that in this case, the radio SED is quite steep. The fact that it's quite steep and it has this little bump could indicate that this AGN this jet might be likely to be an old jet. So it is known from some models that as the jet evolved with time, it might become steeper in the SED. So it seems to be like there are no injection of highly electrons, for example, here. So we could, with some analysis here, we could eventually obtain the AGN, the jet age of this emission here. In this case, this is not one of the most extended. You can see that this is 5 kiloparsecs, so this jet could be something around 5 parsecs extended. Let me show you a few more examples. So here, for example, we have this source that has a very clear jet here and also a hotspot here. This jet is quite narrow, so it could be like a collimated jet. It seems to also be roughly symmetric. And in the SED, you can see a steep SED that becomes flatter towards high frequency. So this might be a retriggered AGN. Then looking at this other example, this example is very curious because you can see that there is some bending here of the jet. So I wondering myself, what is causing this bending to this jet? It might be some environmental effects. And also it's very curious to see that the resolution of the radio contours is not good enough to really resolve this bending. It just looks like some rounding area. The resolution is not great in the radio emission, but in ALMA you can see that we have very detailed resolution to see the bending in this case. The SED of this object looks slightly flatter than the one before. So this might indicate that this jet is younger. These are the two last examples that I would like to show you. Here we have some hotspots that are farther away from the center, so it is brighter at the edge rather than at the center. And if we look at the SED of this seems quite smooth. So that could indicate that this jet was recently launched. In this other case, we have some hotspot that is farther away because if you see the physical scale here is 50 kiloparsecs, so this might be around 100 kpc away from the center. And the SED of this source is very puzzling. It is not so clear. It has like multiple components, but also the fit is not great. So I guess some work can be improved here. That leads me to the end of my presentation. So we have detected 13 jets in ALMA Cal below 0.8 redshift, and they extend from a few kiloparsecs to 100 or more kiloparsecs. In this figure, you can see the radio control, the radio emission of all these subsample. Radio CDs usually indicate that these jets are relatively young. Also, the fact that they are detected in millimeter wavelengths could indicate that are quite young. Some future work would be to investigate potential triggering or quenching by jets or quenching. Explore the AGN filling connections, for example. I will be particularly interested to know, for example, if molecular gas might also be filling the AGN or not, or what other gas phases are filling the AGN. And I will also be very interested in look at the jet interaction with the gas cycle in the ISM as well as the CGM, considering that they are very extended. Now I'll be happy to take questions or comments from you.
Really interesting one. I'm particularly looking forward to the pairing with the molecular gas information. I was wondering, when you do your spectral index calculations, do you separate the different components and fit them separately? Do you match the resolutions? Yeah, that's quite complicated to do with just very close radio bands. I imagine with ALMA, you're muffling.
Yeah, do you mean for the SEV, right?
Yeah.
Yeah. So to be honest, I'm not completely sure how this was performed because it was a quickly assessment. Actually, we don't have the SEVs for all these sources. But yeah, that would be something very interesting to look at. But what would you think would be like the implications?
So, I mean, you will have places where potentially your spectrum is self-absorbed, have a lot of particle acceleration. So some of those electrons might be, some of that emission might be absorbed, and then you would have like an artificial dip.
Right, like something like this, right?
Yeah, exactly. So that could be, that can happen in hotspots, so you have to be careful about that. And also projection effects. If you have something that's very close to your line of sight, it will be artificially boosted. So you might get, you have to try and disentangle that. Otherwise, that could also affect the shape of your SED. Or like when you calculate an average spectral index, it might look steeper than it is in areas. This one you might be mixing pieces. But you can use even just, if you decompose these carefully and match it with the radio data, you can probably get very good constraints on things like, how close to competition you are, constraints in the magnetic field. So there's potentially a lot of science that you can do with this.
Okay, that's very interesting. We could chat later.
Yeah, let's.
I have a question on your CO measurement.
Okay.
And just curious about, do you have cases in which you have a clear line detection serendipitously, but you don't have a redshift associated to it?
Yes, many cases we have just one line, and so we cannot know the redshift exactly one line. So in those cases, we relied on an estimation, a probabilistic estimation of the redshift, and that was based on semi-analytical model.
Okay.
Yeah.
And
so we got some probability distribution of this line, for example, because as could be different CO lines, it's discrete. It's a discrete.
yes. Okay.
And also given the frequency at which it was detected, we have like some probability distribution of this redshift, and we weighted that. So in these error bars is included also the probability of this line to be at that point.
Okay, so the sources without a redshift are included in the plot.
Yes.
With a probabilistic estimates of everything. So okay. And how many are these sources?
So
few percent, 10%.
The ones that didn't have redshift, most of them are.
Most of them. It makes sense because I guess that those who have redshift are the brightest one, the less obscured.
Yeah, some of them had, for example, optical counter. So in that was great because it confirmed the redshift. But in other case, we
and obscured.
Yeah, it could be obscured or at a different redshift.
Are they clear Marcellus galaxies, right?
Right?
They're not AGNs, so
Okay.
yeah, they're galaxies.
But it's the same that you have to rely on redshift.
Well, it was similar to the first question. Do you have information on Your SCD was the total flux. So I was wondering how much spatial information can you do clump by clump and see if it's steepening, if the index is steepening. I mean, you do see evidence for aging. But I mean, I understand there's other effects as well that comes in and
Yeah,
that will complicate the picture.
I see. So we could suggest like performing density fittings in resolved,
Yeah,
is,
as a function of position away from the AGN.
yeah, that would,
Good enough, presumably they are plenty good enough. to do that.
yeah, for sure. We haven't looked at that, but I think it would be very, very.
Having the global flux,
Yes.
especially if there's evolution, then you're mixing all these processes.
You're missing information, right?
It's, yeah, you're putting a deep blanket on many bumps and wiggles, but
Quick question. Are there information about polarization for any of these jets, or is it? What fraction of them is it good enough to do that?
To be honest, I haven't looked at it, but I think would be very, very interesting. So, like to constrain magnetic fields.
Exactly, yeah.
Yes, yes. So I guess, yeah, let's give Victoria another hand. That was great.